Consider two people in separate rooms communicating through a noisy wire. They exchange messages, but the channel corrupts some of the information. The question is, how much does one person's message actually reveal about the others? Not whether the messages look similar, not whether they match exactly, but how much information one truly provides about the other. This is the problem that mutual information solves. It appears throughout machine learning, neuroscience, compression, and representation learning. Understanding it requires rethinking what we mean by relationship between two variables. The intuitive approach is correlation. If two signals rise and fall together, we say they're related. But correlation has a fundamental limitation. It only detects linear relationships. Consider two cases. In the first, y equals x squared, a perfect parabola. In the second, y is random noise, completely unrelated to x. Standard correlation coefficients will be near zero for both. Yet in the first case, knowing x tells you y exactly. The relationship is deterministic. Correlation is blind to this nonlinear structure. This reveals the core problem. Correlation measures whether variables move together in straight lines, but dependencies can take any form: quadratic, exponential, periodic, or combinatorial. We need a metric that captures all forms of statistical dependence, not just linear ones. The solution comes from measuring uncertainty rather than similarity. Every random variable has uncertainty about its value before you observe it. This uncertainty is quantified by entropy. Entropy measures how surprised you'd be on average when you learn a variable's value. If the variable is nearly certain, entropy is low. If it could be anything with equal probability, entropy is high. Formally, entropy is the expected value of negative log probability summed over all possible outcomes. Now consider what happens when you learn another variable. The conditional entropy measures your remaining uncertainty after making that observation. If the two variables are independent, learning one doesn't help. The conditional entropy equals the original entropy. But if they're related, conditional entropy drops below the original. The difference between these two is the information that one variable provides about the other. Mutual information is defined as this reduction in uncertainty. Start with your initial uncertainty, then subtract the uncertainty that remains after learning the other variable. The difference is mutual information. This can be rewritten in an equivalent form. Mutual information equals the expected log ratio of the joint distribution over the product of marginals. What does this mean? It compares two probability distributions. The joint distribution describes how the variables actually occur together. The product of marginals represents what the distribution would be if they were independent. The log ratio measures how far reality deviates from independence. If the variables are truly independent, the joint equals the product, the log becomes zero, and mutual information is zero. If knowing one variable substantially changes the probability of the other, the log becomes large, and mutual information increases. Mutual information is always non-negative, reaching zero only under complete independence. Let us work through a numerical example. Consider two coin flips that aren't quite independent. Each coin shows heads 60% of the time and tails 40% of the time. But there's a twist. The two coins are slightly correlated. Both showing heads happens more often than you'd expect from pure chance. We start by computing the entropy of the second coin by itself, which tells us how uncertain we are about it before seeing anything. This comes out to approximately 0.97 bits. Now the key question. If we observe the first coin, how much uncertainty remains about the second? When the first coin shows heads, the second coin becomes more predictable. When it shows tails, the pattern shifts differently. Averaging over both cases, the remaining uncertainty drops to about 0.71 bits. The difference between these two numbers is the mutual information, approximately 0.26 bits. In other words, observing the first coin reduces your uncertainty about the second by about 1/4 of a bit. Not a huge amount, which makes sense because the correlation is modest, but it's clearly non-zero, confirming that the two coins share information. Mutual information provides a universal measure of dependence. Unlike correlation, it captures all statistical relationships, linear or nonlinear, simple or complex. It measures not similarity, but reduction in uncertainty. This generality explains why mutual information appears throughout modern data science. In feature selection, it identifies which inputs genuinely affect the output. In representation learning, it measures whether embeddings preserve meaningful structure. In neuroscience, it quantifies how much information a neural response carries about a stimulus. In compression, it determines the theoretical limit of lossless data compression. Mutual information teaches us to think about relationships not as coincidence or similarity, but as shared predictability. The more one variable reduces uncertainty about another, the more information they share. Thank you for watching. We hope this video provided a clear and intuitive explanation of mutual information. If you found this helpful, please subscribe to our channel for more content on related topics. Your support helps us create more in-depth educational material. You can also support us on Patreon, where you can suggest future video topics, ask questions directly, and receive early access to new content.